I am going to give one simple example for this type of a reducible Markov chain with the transient states and one or more absorption state. I am making the assumption that is a positive recurrent. So, instead of positive recurrent I have a finite Markov chain. So, the finite Markov chain at least one state is a positive recurrent. Therefore, this is both are going to be a observing state, therefore, you do not want those conditions also. So, here this in this model the states 0, 1, 2 are the transient states, 3 and 4 are observing states. This is a easy example in which you can visualize someone is doing the undergraduate with the probability of he is not able to complete the undergraduate in the next step with the probability of he is moving into the postgraduate in the next step. So, I am making a DTMC with the assumption the memoryless property is satisfied and so on. From the postgraduate either someone gets the job 1 with the probability 1/3 or not able to complete the postgraduate, that probability is 1/3, or he completes and go to the PhD program 1/3. From the PhD 1/4 is not able to complete the PhD in the next step, or with the probability 3/4 he is getting the job 2. Now, you can visualize the questions. What is the probability that I observed into the state job 1 or job 2? That is a probability of absorption. The next question, how much time on average I will be spending in the transient states in the study before I get the job. So, this is the way you can visualize the reducible Markov chain with this type. So, these two questions are going to be answered by finding the probability of absorption and the mean time up to absorption. First, let me write the P matrix in the canonical form, and all the submatrix I made it in the different colors. So, 3 and 4 are going to form a, each one is going to be observing states. So, therefore, A to A, that is identity matrix, A to capital T, that is a 0 matrix submatrix, then T to A, that is again a matrix, that is R, then T to T, that is a Q matrix. So, what we need the Q matrix and the R matrix, both are submatrix of capital P, that is a one step transition probability matrix. So, you find out what is I minus Q, I is identity matrix of the same order, I3 here minus Q matrix. So, you know the Q matrix is this. So, I minus Q matrix, find out the inverse, that inverse is this much. So, from this if you multiplied the vector E, that is 1 1 comma 1, you will get the mean time to absorption. And also you can find out the probability of absorption after finding the I minus Q inverse, that is a fundamental matrix multiplied by the R, this matrix, you will get the probability of absorption. I am not giving here the numerical calculation. See the result. So, this is the mean time up to the absorption, and this is the probability of absorption. First, let us discuss the probability of absorption. If the system starts from the state 0, state 3 is nothing but the job 1. So, with the probability of you would have been observed into the job 1 with the probability of, if the system starts from the state 0 from the undergraduate. Similarly, with the job 2, that probability is off. It's a probability mass function, either you will be in the job 1 or job 2, that is a probability of absorption. If you would have starting with the postgraduate, then with the probability off and off you may be in the job 1 and 2. Whereas, if you beginning with a PhD program, not these two programs, that is not possible, but still this is just example. So, if you start with the PhD program, then definitely you will end up with the job 2 with the probability 1, because there is no arc from 2 to 1 and will end up the job 1. Therefore, the probability of absorption into the job 1 that probability is 0 is for illustration. Therefore, you can make out how the calculation goes. So, here the probability of absorption starting from the state 2, that probability is 0 to the job 1, whereas job 2 that probability is 1. So, this is the probability distribution of probability of absorption starting from these transient states. Similarly, you can visualize the mean time up to the absorption. These zeros can be discussed first. So, if the system starts from the state 2, what is the average number of steps the system goes from the state 2 to 0, then it goes to the absorption state. That is not possible, the system is going from 2 to 0. Therefore, the mean time is going to be 0, because the minimum time is 1, or minimum number of steps system spending in the transient states are 1 and so on. Therefore, mean is 0 here. Similarly, the system is starting from the state 2 and land up 1, and from there it goes to the absorption state. That is also not possible. Therefore, that mean is also 0, whereas all other values the greater than 0, that gives what is the average number of steps the system is starting from these transient states and reaching these transient states before absorbed into any one of the absorption states. Accordingly, you will have these values. With this example, I go to the next example, that is a reducible Markov chain, and this is a special case of a random walk also. Let me discuss what is the example. This is called the gambler's ruin problem. Let me define what is the gambler's ruin problem. Consider a gambler who starts with the initial fortune of rupees I amount he has at the time 0, and then on each gamble either wins rupees 1 or loses rupee 1 independent of the past with the probabilities p and 1 minus p respectively. So, in this game there is no draw, there is no tie, either he wins or he loses. Wins with 1 rupee, loses 1 rupee, and the corresponding probabilities are p and 1 minus p, and he started with the initial amount small I, and Sn denote the total fortune after the nth gamble. That means S naught is a small I, and S1 becomes a, if he wins, his total fortune after the nth first gamble, that will be I plus 1. If he loses, then his money would have been I minus 1. That is the way S1, S2, S3 sample paths goes. The gambler's objective is to reach the total fortune of rupees capital N, where N is a some number, some positive integer, without first getting ruined. That means you can make a state transition diagram for this Markov chain. The Sn is going to form a time homogeneous discrete time Markov chain because of each games are independent, and with the probability p and with the probability 1 minus p, he wins or he loses. Therefore, the Markov property is going to be satisfied. Therefore, this stochastic process will form a discrete time Markov chain. If you notice, if he is land up 0 amount at the nth game, then he is ruined. If he is getting a first time n rupees, then the game is over. That is subjective. Therefore, this is a special case of a random walk, one dimensional random walk, in which the states 0 and n are going to form a observing barrier. Once the system goes to the state 0, the system is absorbed in the state 0. Once the system reach the state capital N, then the system is observed in the state N. Therefore, the states 0 and N are observing states, and all other states are states from 1 to N minus 1 are going to be the transient states. Therefore, this DTMC is a reducible DTMC with transient states and 2 observing states. So, this will fall under second type, the one we have discussed. Our interest in this model is what is the probability of absorption, what is the probability that he loses all the money at the end of some game, or what is the probability he reaches a capital N, that is his objective. So, that is the probability of absorption. The other one is how much time he is in the transient states on average, what is the mean time of absorption till he reaches the absorbing states either 0 or N. So, for that I am making the notation first P suffix I, that denotes the probability that the gambler wins when S naught is equal to I, that is I. I means initially I amount he has, that is S naught. So, what is the probability that a gambler wins? Clearly P naught is equal to 0, similarly P n is equal to 1, because no way, if he is having initially 0 amount he cannot win, therefore, that probability is 0. If he is having initially, the gambler has the amount n amount in at the time 0 itself, then he need not play at all, therefore, that probability is going to be 1. Therefore, the probability the gambler wins, that probability is going to be 1 if he is having n amount initially. For all I in between 1 to n minus 1, you can make a recursive relation using the Chapman-Kolmogorov equation. That means the probability that the gambler win with the I amount initially, that is same as either he has initially n plus 1 I plus 1 amount initially, and with the probability P he wins, or with the probability I minus 1 the gambler wins multiplied by the probability Q. Q is the he loses. So, these two combinations will give the probability of gambler's win. You can do the simple calculation, the way we have PI's in terms of PI plus 1 and PI minus 1, you can write a PI minus 1 also, then you find out the difference, then you will get the recursive way, and you will get in terms of P1 and everything you will get it. So, you can use a P capital N is equal to 1, using that you will get all the PI's. You can use this relation P naught is equal to 0 and capital P n capital P capital N is equal to 1. Using these two values, you find out the difference and you make a recursive relation, you will get a PI's. So, whenever the P is less than Q and P is greater than Q, you will get, and the PI's is 1 minus Q minus P power I divided by 1 minus Q power P power N. For P and Q is equal to same, that means it is off, because Q is 1 minus P. Therefore, you will get the probability of gambler's win, that will be I divided by N, that you can get. And here the interest is what is the probability that he is going to win. That means this is the probability that he is going to win, and the 1 minus of that is going to be the probability that he is going to win in this game. The next one is our interest is mean number of games, because the objective is he has to reach the capital N amount. So, the game is going to be over, either he completely ruin or he is going to get the N amount. Therefore, I am making here the random variable m suffix I, this is suffix I. So, m suffix I is denote the number of mean number of games, I am directly making a random variable for mean suffix I, and I know the relation for this, and here also I am making the similar relation. By solving that I will get the MIs. So, this is the mean number of games in the mean number of games played by the gambler until he goes to broke or wins completely fortune n. So, in this lecture I have discussed the reducible Markov chain and the types of reducible Markov chain and some examples also, and finally, I have given gambler's ruin problem. References are this. Thanks.